Okay, folks, we're moving on to problem number 12. And this one, we're talking about a random sample of 100 of last year's model car had 20 had a specific minor defect in the brakes. 20 out of 100 cars had a minor defect in the brakes. That have been really minor defect. So the automaker decides to change the production process. Good idea. And then they go out and they find that 50 of the 350. So they go out to a larger sample of 350 and 50 of them. Oh, great job. Now it's only 1 in 7 instead of 1 in 5. Yeah, it better have been a really, really, really minor problem. Okay, so the question is, was it successful? It's another fancy way of saying, has the proportion changed, right? And when they're saying, was the company's adjustment successful, what are they trying to do, folks, right? They're trying to lower the proportion of defects in these brakes, right? So we know it's one directional because we don't want to talk about two directional. They're only going to be successful. It's actually going down, right? So they want the fact that the new one to be lower than the old one. So we'll have to word that carefully, okay? So they asked us to perform a test to support the answer. So we have to do a whole significance test. So we're going to see if the change was meaningful or not. Okay, so we're going to carry out a significance test, and we kind of have this hypothesis here. The hypothesis is that they were completely unsuccessful. So 1 and 2 would be fine. Do it last year's and this year's. I don't like L and T, so we'll just use 1 and 2. Okay, so 1 is that. And then we're going to say 2 has the proportion gone down. So if we wanted to go down, basically we'd say P1 is this year's true proportion of brake defects. And piece of 2 is last year's. So we are hoping that P1 right, this year is lower. The proportion of defects is lower than last year. Okay, so that's why we had this direction here of less than. So what are we going to do? Well, we're going to have a 2 sample. We're calling this. We'll do a z-test. I can call it z-test. I was going to write out significance test, but we can say it's a z-test because we're using z. Remember, when we use z, we're using proportions, right? Okay, 2 sample z-test for proportions. Awesome. Okay, let's check some. Oh, we should get an alpha, right? When in doubt, 0.05. Okay, so let's check some conditions. Well, first of all, do we have random? Yeah, they say they were randomly selected cars in 2 independent samples. Right, the 100 cars that were selected for last year and the 350 cars that were selected for this year are not related to each other. They're not like brothers or anything like that, right? They were, the 10% is going to be met because even though they sampled without replacement, you got to assume that these automakers not just making 400 cars, right? You assume we're to say that we're assuming that 100 and 350 are much less than 10% of total cars made. So we'll make that assumption. I mean, it's a car maker. They don't really make small sets, right? It's not like some guy who's going out and saying, "Oh yeah, I'll make 100 cars." No, they're making a lot more than that. And then we have to check to make sure that we're meeting the large counts. So, well, how do we check large counts? The large counts is met if all of these are greater than 10, right? All of these. And it's not that bad to do, because they all have to be greater than or equal to. And show the math, folks. This is 20, right? Why? Because there was 20 that were successful, then the 80 were non-successful. In this case, the 80 was the success, right? Having the defect is but we just say P is successful. So obviously I would call this be more successful than the 20, but if we're calling P probability of success, in this case 20 and 80 and 50 and 300. Remember, just because you want something to happen. Like the car company would much rather have a low number here. Success is really not having a defect, right? Having a defect is kind of a failure. But remember, whenever you measure P, that is quote unquote the success. So they're all good. So we're met. So we're good to go. Now we will start doing some work, right? We're going to do some work. And our test statistic is going to be the difference, the true difference, minus the hypothesized difference. This is almost always 0. It's whatever this number here is 0. That's going to be 0. It's over the standard error. And remember, the standard error is our approximation. Now, what we'd love to be able to do is know what the true proportions are, but we don't know. And because we're doing a hypothesis test, we're assuming that they're the same ones. So we have to figure out this p hat. So what's going to go in here is going to be this p hat. And this is what the hypothesized true proportion would be. Right? We don't know what this is, but we can take a guess, right? We can just say, well, we'll take a guess. So it's going to look like this. And hold on. So this is what we're assuming it would be, right? This is the total. If it was all from one pool, we would assume it's going to be 70 over 450, which I just did on a calculator. 0.155555555. So therefore, when we do this calculation of the standard error, it would be 1.5. I'll round a little bit in here. Now again, we got to remember that this would be different. This would be different if we were doing a confidence interval. Okay, folks, if we're doing a confidence interval, we would not be making this assumption. This assumption we did right here would not happen if we were doing a confidence interval. We'd have two different p hats here. But because we're assuming they're coming from the same pool, we are going to therefore figure out what that proportion, what that sample proportion would be, and we're going to use that for our standard error. Okay, so our z-score is going to be, I'm definitely going to need to jump over to the calculator for this, but the P1 was what? P1 was 20 out of 100. Did I reverse this? I think I reversed this. P1 is this year. Yeah, I reversed this here. You have to change these around a little bit. They were all wrong. They were backwards. This should have been 50 because this is this year. This should have been 300. This should have been 20. This should have been 80. I mean, I don't think I would have lost points, but as long as I have it right here, which I think I do now. So this year was, what, 50 out of 350. That's 0.14 something. It's like 1/7. I'll get the exact number in a second. 1 out of 5. And we'll jump over and get this in a second. So, I mean, I'm doing all this out. You're going to see in a second we don't need to do all this out. 0.1428. So I'll just call it 1.4. There's where I want to be. Okay. And then we have to find the standard deviation. What's a 0.15? So I just did 0.1555 times 0.84555 divided by n1 plus, actually it's really n2, right? You reverse the 2, plus 0.1555 divided by 0.84555. And I got our standard error 0.04112. So to find our actual z-score, we should be taking this try to use the mouse and it didn't work, so we'll just do it this way. Divided by subtract 0.2, and then we take this and hit enter, and we divide it by our standard error, and we get our score of negative 1.39. I should have just put that in here. What was the negative? What was it? 0.04 something? 0.0411. Okay. So negative 1.39. Doesn't feel significant, does it? When I think of negative 1.39, I don't think it's going to be far enough to hit that 5% threshold. I mean, I want to see 1.7s, 1.8s. I want to get closer to 2 to be significant. But let's just check. We'll see. So let's look up real quick. If you remember, one of the things that we have is we want this to be less than. So our normal CDF is we're going to be looking this area over here. Right, negative 1.39. So our p-value is going to be that. So our p-value could be normal CDF, negative infinity to negative 1.39, comma 0, comma 1. Okay, the 0, comma 1 is kind of default. So let's see what this p-value, I doubt, I really doubt it's going to get there, but we'll see. To negative 1.39. And the answer is 0.0822. So our p-value is 0.0822. Okay, so all this editing in green, I just want to show you that this is all the work that you need to do to kind of get full credit to know that you're understanding something. But the reality is the calculator does this for us, right? So let's come back here. Just want to make sure that we all could have done this with the calculator. If we go to stat test, we want to do a 2 proportion z-test. So they're going to ask us how many were successful. Well, the first one was 50 out of 350. That was this year. And what was last year? Last year was 20 out of 100. And we were seeing the less than version, and we're going to calculate this. And there's that 0.0822, isn't it? Isn't that gorgeous there, that 0.0822? So we could have got it that way just as easily instead of doing all the work out. But I want to show you all the work and all the steps that you have to do. So now let's go back and finish this puppy up. The last thing we now need to do is we now need to conclude. And what color didn't we use? Did we use purple? I don't know if we used purple or not. So now, because the p-value is greater than our alpha, we fail to reject the null. Now, the null is not true. We just don't know. We don't have evidence that it's not true. So it's not true. But therefore, we can just say we don't have convincing evidence that the car company has changed defect rate in their brakes. Right? That's kind of concerning, right? You would think that they'd fix that. Okay, part B. Based on your conclusion in part A, which mistake, a type 1 or a type 2 error, could have been made? Well, remember, type 1 is accidentally accepting the alternates. You can only make an type 1 error if you've accepted the alternate. We have not accepted the alternate here, so the only mistake we could have made is a type 2. We could have made a type 2. What are consequences of this? Well, the consequences are the company thinks that they need to do more work to fix the machines, when in reality the work they did was successful. So they made improvements, but they don't think it was improvements. So they go back to the drawing board. If you ask me, 1 and 7 is not good enough. They should go back to the drawing board anyway. Anyway, folks, that's number 12. We'll get to number 13.